Hello, everyone who's just joining us now. We're really pleased to welcome you to the final installment of the series of different webinars that the BioRecover project has been organizing related to critical minerals and microbiology and the intersection between those two fields. So today we're really excited because we have an all-star panel of really top-notch scientists from around the world who are working on bioleaching and the ways that that can present a solution to the resource challenge that the planet is facing. And the topic for today's webinar will be, how can microorganisms contribute to a responsible mining future? And we'll be focusing on both the environmental and social impacts of bioleaching. So just to get started, I wanted to give a quick overview of the stakes that are at play when we talk about critical minerals and microbiology. So right now, we see that the COP28 conference is winding up. And I think it's important that we keep in mind that in order to meet the climate goals that the planet has set for ourselves, and to transition away from fossil fuels into a carbon neutral economy, we're also going to need to transition the materials that we use to power the economy and the renewable energies that drive our daily lives. And so here on the left, you can see the projections from the International Energy Agency about raw material demand going forward, meeting either the 1.5 or 2 degrees heating scenarios. And you can see that there is an exponential increase in demand for a wider range of different raw materials, particularly battery metals, but also base metals, aluminum. Yeah.
We are still on your first slide.
Can you see my second slide or no?
Not.
Okay. Can you see it, Ella?
Yeah.
Okay.
Yes, now it goes. Thank you.
Great. Hopefully the technical problem will be sorted out. So sourcing all these materials comes with a cost, though. And that cost is notably in terms of the amount of waste products that producing raw materials generates. And so just the waste product from aluminum, which the BioRecover process is looking at, which is called bauxite residue or red mud. Annually, the amount that's produced around the world is over 3 billion tons. And that's rapidly increasing. And so we've seen numerous examples of the challenges that mining waste can pose when it is improperly handled. And we know that as the demand for raw materials continues to increase, we're going to see increasing amounts of raw materials, and that's compounded by the fact that the concentrations and the grades that we're looking at in the deposits that are being commercially exploited are decreasing and becoming more complex as well. And so mining waste is posing a real environmental challenge around the world, and that can have catastrophic consequences, as we've seen here, for instance, in the image from the Brumadinho Dam in Brazil, which collapsed tragically several years ago. And we know that sourcing raw materials to meet the energy transition needs will also pose numerous social consequences. We know, for instance, in Europe that there's been several really large demonstrations against new mining projects. Here we have an image from Serbia in the past few years where there was mass demonstrations against a proposed lithium mine in the country. And so we're hoping to address a few of these different issues in the webinar today. And that is really also what the BioRecover project has been working to do over the past 4 years. So BioRecover brings together 14 project partners from across Europe as well as South Africa. So today we're really happy that our colleague Cello will be representing the partners from Wits University in South Africa. And it brings together practitioners working in the mining industry, as well as microbiologists, chemists, engineering firms, and experts in process development, as well as downstream stakeholders in the value chain as well, including an automotive OEM. And we're looking at taking extractive wastes from 3 different industrial feeds and transforming those extractive wastes using biotechnologies in order to produce critical raw materials. So specifically, the BioRecover project is working to extract rare earth elements from bauxite residues. Those are being sourced in Greece. Platinum group metals from low-grade ores in South Africa. And we're also looking at producing magnesium metal from low-grade magnesite ores that are sourced in Spain. So you may hear a little bit more about the project when Cello presents her research. And we also are really pleased to welcome 2 guest speakers as well into the webinar. So we have Nadia Mikichuk, I hope I pronounced that correctly, who is the CEO and president of MIRARCO, which is the Mining Innovation Rehabilitation and Applied Research Corporation, based in Sudbury, Ontario, Canada. And she's also the executive director of the Goodman School of Mines at Laurentian University. And she has 18 years of experience working in environmental microbiology with a focus on mining systems and the development of bioleaching and bioremediation technologies. So thanks for joining us, Nadia. We'll hear from you in just a second. And we're also really pleased to welcome Patrick de Hugues from the French Geological Survey. So Patrick is a microbiologist with an engineering degree in biotechnology and a PhD in applied biotechnologies on process optimization, and has done postdoc work at Warwick University on high temperature bacterial leaching. Patrick joined the French Geological Survey, BRGM, in 1999, and as we'll hear from him in a little bit, spent some time in Uganda working on the first industrial plant reprocessing cobalt using bioleaching technologies. And currently, Patrick is the head of mineral resources and circular economy, their scientific program at the French Geological Survey, and is in charge of coordinating BRGM scientific activities regarding responsible and sustainable raw material supply. So we're really excited to have Patrick speaking today as well. And last but not least, we have Cello Ndlovu from the Wits University in South Africa. So Cello is a professor in the School of Chemical and Metallurgical Engineering at the University of Witwatersrand in Johannesburg. She currently holds the Department of Science and Innovation and the National Research Foundation funded research in hydrometallurgy and sustainable development at the university. And in 2022, she was recognized by the National Science and Technology Forum in South Africa for her contribution to research and development and human capacity building in the field of hydrometallurgy. Cello is also a former professor at the Southern African Institute of Mining and Metallurgy, and looks after the interests of the mining sector professionally in South Africa. So we're really happy to have all 3 of our speakers on board today. And without further ado, I will pass the floor over to Nadia, who will be giving us a little bit of an introduction into her work. So the floor is yours, Nadia.
Thank you so much, and thank you for the invitation being here today. I know that the BioRecover program has a lot of international partners, but Canada is not among them. So I thought I would give a little bit of context as to where we're at in Canada and North America in applying biomining. So a few perspectives. We'll go to next slide, please. So the challenge of meeting critical mineral needs is, of course, a global problem. You could argue that Canada is a bit behind the global average, certainly the European and South African and Australian average in applying biomining. We are now talking about it at a federal and provincial level. So we have 10 provinces, 3 territories, sorry, and all of them now have been reflected in what we have as the Canadian Minerals and Metals Plan. Now, that is a Canadian federal initiative to look at means of meeting these critical mineral needs, targeting various areas that have to be advanced in order to supply the demand. that is happening. And that spans, of course, from enhancing exploration, developing deposits. Canada is very rich in its mineral resources. We have all of the critical minerals well reflected in deposits that have yet to be produced. We, of course, have a lot of very large ore bodies that are already producing, Sudbury, Ontario being one of the largest nickel producers, but our ore deposits are going deeper and improving processing. One key area that, of course, would be an area of interest for everybody on the webinar today is that a lot of the discussion, both in the minerals plan at the federal level and also provincially, is looking at circularity and addressing our wastes. And this is very new for Canada. So we have a very large landscape. We have a lot of mines that are in very remote areas. And you could argue that a lot of our tailings and mine wastes are out of sight, out of mind. And because we haven't had the pressure of communities, although we do have a lot of First Nations communities that are impacted by these remote mines, it hasn't been front and center in the discussion in going back and reprocessing these materials, even from just an environmental perspective. But all of that is changing with the push for critical minerals. And now we have both a pan-Canadian strategy on mining value from waste, our provincial plans that oversee mining jurisdictions within each province have a critical minerals strategy. And a lot of that is now starting to look at new, innovative, new bioleaching technologies, many of which have been applied globally for some time, and trying to start tackling the problem that really hasn't been addressed in Canada in mining value from waste. So if we go to the next slide, please. So compared to all of Europe, Canada is sort of on par with the amount of material that we produce, waste material, I should say. So we have currently in Canada over 200 active mines. The range of abandoned mines, we have a very long history, young history, I should say, relative to Europe. I guess we're quite young still, but over 100 years of mines going bankrupt. So we have an inventory of 10,000 to about 15,000 abandoned mines, many of which do have significant stockpiles of waste materials. We do produce annually about 650 million tons of tailings deposited across the entire Canadian landscape. And really that presents a large liability. And so Canadian mining regulations and environmental regulations are quite strong. And so that means that many of the mining companies that operate in Canada actually have to pay upfront what is called a financial assurance to cover the costs of closure so that we don't keep adding to that very long list of tailings liabilities and environmental liabilities. But what that means is that these mining companies are already paying a very high price for these waste materials, and that can be prohibitive to expanding and growing new mining operations. So if we go to the next slide, please. So if we look at that opportunity now, and sort of the topic of our discussion today, and looking at how we can address some of that environmental and costly financial liability, and actually look at the opportunity that exists in those wastes. So in Sudbury alone, we have one of the largest stockpiles of sulfidic mine waste in all of Canada. We can estimate that over the 120 years that we've had mining in Sudbury, there's about $8 to $10 billion worth of nickel, the equivalent again in about cobalt and copper present in mine tailings ponds in the region that I'm currently situated in. You can expand that out to other metals. Gold, of course, not a critical mineral, but a significant stockpile there as well. Copper and other critical minerals are reflected in many of the materials that we have already milled sitting at the surface, but not necessarily economically viable in terms of other reprocessing. So given this whole push for critical minerals, we really now have that opportunity to discuss and adopt biomining, bioleaching, and other hydrometallurgical approaches to try and address this long-term issue. Next slide, please. So, of course, I think everybody here knows this. The difference between the ore and the waste is really a cost of extracting that value. We know that biotechnologies like bioleaching have been shown to be economically favorable. The challenge really now is not just showing the robustness of that bioleaching component, but understanding that that one component is part of a very large flow sheet. And I think part of the discussion that we have to have when we talk about introducing biotechnologies for reprocessing something like these pyrrhotite tailings that I'm showing you here, we can cover some of the cost of the reprocessing with that, 0.1 to 0.9, 0.9 is the high end, copper, nickel, and cobalt. But if we don't address the rest of that 99% volume, extracting other lower value, higher volume materials, in our case, we have about 30% iron and sulfur in this content, in this tailings. And that content, of course, even if we have commodities that aren't high value, we have to think about moving towards a zero waste solution. So the bioleaching is one piece, but we have to think more holistically and not be putting all of that material back into the tailings ponds. Next slide, please. So one of the ways that we've been focusing on, both in my research program and amongst my team, is ensuring that these biotechnologies, when they finally do make their introduction into the Canadian mining landscape and mineral processing operations, is that they are robust. And we've been using molecular technologies and genomics to help us refine and control the black box of microbial communities that drive these bioleaching processes, and ensuring that they in fact are reliable and giving us consistent recoveries every time we apply them to pretty heterogeneous old tailings materials. Next slide, please. And so one of the challenges, and of course, getting biotechnologies into application, of course, we can demonstrate them well on the lab bench. We can publish those scientific papers, but in getting it into industry, there are those key scale-up technology demonstrations that are required. So we move from bench scale. We have to assure that for the heterogeneous materials that might come in that you see at the top of the slide here, that process works at batch scale, usually small bioreactors, scale that up into a semi-continuous system that mimics what it would look like at full scale, and then move to a demonstration type project that can show and provide reliable kinetics and other data that can be used by the mine operator to see if this is a viable flow sheet for them. And all along the way, the biotechnology piece has to scale, as do all the other components. Next slide, please. And so that's really what we've been focused on. And again, as I mentioned, in Canada, we really don't have a lot of technology companies or mining companies that are already using bioleaching in their operations. And so we're working closely with our mining partners that are now very keen to look at the opportunity of reprocessing their mine waste materials. And we're trying to support that scale up that is critical to getting technologies through from the lab bench into operation. Next slide, please. And so just my final slide here, in looking at a key piece that Marco and my team are developing. Academic institutions and industry sort of cover either ends of that gap, but filling that gap, we need a facility to be able to pilot and scale up those technologies. So we are building a Center for Mine Waste Biotechnology here in Northern Ontario in Sudbury. Our capital campaign is underway, and we're hoping to break ground in 2024. So excellent facility that we hope to have available for opportunities, and hopefully engaging with some of our European and international, South African and Australian and global partners in building BIORECOVER type projects in Canada. Thank you very much.
Great. Thank you so much, Nadia. That was really interesting to hear the Canadian perspective, and also quite exciting to see what's coming up in 2024. So just to keep us on time, I will pass the floor over to Patrick, and then we can hear about your experience working with biomining as well. So Patrick, the floor is yours.
Can you hear me now?
There you go. Yes, we can now.
You can. Very good. And can you see the presentation? Yeah.
Yes, we can.
We can see your slides as well.
Okay, very good. Okay. Hello, everyone. Good evening or good morning, I don't know. Thanks very much for the invitation, and especially hello in the room. I saw my friend Mark Thompson, so special hello to Mark. Yes, I was asked to present to you an experience that BRGM ran quite some time ago now, because it was around 2000. And so the presentation is basically a old case study, a old story, but still I think one of the few examples of reprocessing of mining waste using bioleaching. And I think what we learned at the time is still up to date. So the title is Reprocessing of Mine Tailing Using Bioleaching from an Industrial Application in Uganda to EU Challenge. Sorry, just struggling to get it. Okay, so the story is the story of a former copper mines that generate some tailings that themselves generated an environmental issue. Basically, the Kilambe sulfide deposit in Kasese in Uganda was mined for 26 years, produced a lot of copper, and left aside a cobalt-rich pyrite concentrate that was stockpiled at Kasese. In the area, there is heavy rainfalls, and the pyrite concentrate disperse downstream from the site, and as well as that, there were lots of acid mine drainage phenomena that took place in the area. And as you can see on the pictures, it's sort of destroy downstream from the area a lot of natural ecosystem. And an important aspect in the project was actually that this area was the Queen Elizabeth National Park. So what happened at the place in the time? Well, what happened on the place was nothing but an acid mine drainage. And what's acid mine drainage? And I guess most of you knows that. It's the microbial degradation of sulfidic matrix from rocks. It's connected to biooxidation of ferrous iron and sulfur. It produces sulfuric acid, and this oxidation of the sulfide liberate or solubilize the metals in an acidic media. In Kasese, the amount of concentrate available on site was approximately 900,000 tons of concentrate, of mining waste, containing 80% pyrite. So you can imagine the huge acid mine drainage which took place in the area. But there were also in this pyritic matrix something like in between 1.3 and 1.4% of cobalt. So at the time, the question was, why not optimizing the natural bioleaching potential? That was very obvious on site by developing a process that will both remove acidity potential and metal contamination risk by treating the sulfidic part of the tailings, and at the same time producing metals. And as I told you, it was cobalt, of course, but it was former copper mine containing also, of course, some remaining copper and some nickel. So basically, the time for the project to go from the laboratory first experiments up to the industrial scale was 10 years. 10 years in which BRGM developed the processes at different laboratory scales, from a couple of milliliters up to 5 cubic meter on BRGM site. And then we had a pilot operation in 93 in Uganda to actually test the process on site. And then the flow sheet and the global flow sheet was designed, and the plant started in 98, 99. What's important, and I think it was already said by Nadia, it's that bioleaching, as you can see on this flow sheet description, is only one part of the global approach and of the reprocessing. So the project lasted for 12 years. 12 years of production from 2000 to 2016. Don't be surprised. You're going to say, but I don't know how to count in France, but it's not that. It's the plant started in 2000 and stopped for 4 years when the cobalt price was not high enough to justify the profitability of the process. And so it stopped for 4 years. And then when the cobalt price raised to a normal level again, then they restarted the plant. That's an advantage of treating bioleaching. It's that it's very robust and flexible type of processes. And I put here the question of, is this case the ideal case of mining waste reprocessing? And one aspect of it is, of course, a lot of cobalt was produced, but the fact that 99% of the remaining waste is still in place. We replace sulfidic waste by less harmful waste for sure. But at the end of the day, it's what you can see here. You can see downstream from the I don't know if you can see my my mouse here, but you can see two big ponds for taking the new waste generated by the processes. Basically, the cobalt, all the metals were valorized and sold, but we had 1 million ton of sulfidic, very dangerous waste, and now we have 1 million ton of ferric waste that are not harmful, but they're still there. And I think that was mentioned already. It's part of the challenge for bioleaching and any reprocessing. It's to actually treat not only the metals, but the materials. So that's the conclusion. Reprocessing and bioleaching is definitely a solution when you face mine waste, but it's not the solution. It's not the only solution. What are the opportunities? Well, of course, production of metals and minerals. And again, that's very important. We have to look at both without mining, because most of the time the concentrate are already grinded, or the waste are already grinded. So it's of course a lot of gain when you look at the energy, for example. Of course, it's a better management of metal contaminants and acid mine drainage. It's definitely an opportunity when you use bioleaching. And it's a potential solution for remediation and land use. What are the challenges? Well, the challenges is the raw mobilization of contaminants. When you're going to act on a mining waste, whatever you do, you're going to put in place a process with the associated risk. So that's one important aspect. The profitability is always a question. There is some administrative and legal framework that you need to take into account. You know, it's sort of a mining activity, so it's still a challenge in some countries. And of course, like any mining activity, you have the social perception and acceptance, which is still a real question, even though you are doing reprocessing. So reprocessing is an option for managing environmental impacts and potentially financing remediation action, for sure. It is also the integration of the concept of circular economy at the mine level, and that's a very important aspect to actually optimize the use of the material that you have mined. So I think bringing the circular economy concept at the mine level is of extreme importance. And in some cases, not all of them, it can be also a profitable industrial metal production operation. And thanks very much for your attention. I hope I was quick enough, because I think we were given 10 minutes, so I think I did more or less.
Thank you very much, Patrick. That's a great case, and it's always useful, I think, to have a specific example. And thanks as well for highlighting some of both the benefits and the challenges related to biomining. I think we will now pass the floor directly to Sela and allow her to present your work.
Let me load my presentation. I did make a bit of changes, so I hope it will come out fine. I don't know if you can see it.
Yes, we can. If you'd like to go in full screen.
Is that in full screen now?
Yes, now it's good.
Oh, okay, sure. Okay, So I'm going to present on some of the work that we've been doing related to the BioRecover project. So in my school, or in South Africa, okay, maybe let me just say good evening and good afternoon and good morning to everyone first before I start. So we have been doing a lot of PGM processing, but using chemical processes directly, because we have not really done bioleaching as such when it comes to PGM processing, because PGMs are actually very refractory to treat. They're very difficult. So having a project on bioprocessing was quite challenging and exciting for us to embark on, because it's something that really has not been done because of the fact that the PGMs are quite tough to work on, especially if you're looking at raw minerals or virgin ores. So we've been working on this project through the BioRecover. So if you look at the generic mining and metal extraction processing chain, where actually the PGM processing would follow, you can see that you have the mining, which is usually with PGMs is underground. And there you are going to have a lot of water that is actually used. So you find that the PG mining activities, you use quite a lot of water, approximately about 273 to 544 cubic meters per kilogram of PGM that you are going to produce for the whole process, for the whole value chain. And then you also look at the beneficiation process. So you do the mining, you do the beneficiation, comminution concentration. Then it is followed by pyrometallurgical processes where you do the smelting, and then you do the hydrometallurgical processes where you firstly remove the base metals, and then followed by the PGM processing. So you find that this whole process is it uses a lot of water, it is energy intensive, there's a lot of waste that is produced, and there's also some carbon dioxide emissions, about 40 to 50 tons per kg in the whole process. So in terms of the bioprocessing, like I said, there's really not been much that has been done looking at the bioprocessing of PGMs because of the fact that PGMs are quite refractory. There's some chemical processes that have been tried, like the KEL process, the Apion process, that have been tested, but there's nothing that is really there that bypasses the pyrometallurgical step and you go directly to a hydrometallurgical process because of the mineralogical composition of the PGMs themselves. That makes it very difficult to actually do a direct hydrometallurgical step in order to recover the PGMs. So in the bioprocessing project that we've been doing, we have looked at based on the mineralogy of the material, we had to come up with a process route that was going to consider all the challenges in terms of the mineralogy, specifically in terms of the mineralogy, since the PGMs are quite refractory. So in terms of the project itself, we had to look at the isolation, selection, and screening of indigenous microorganisms from a platinum mining site, because we wanted to look at microorganisms that would have been adapted to a PGM mining environment from the start. And then the second phase of the project was then the biobeneficiation of the feed materials through bioprocessing to remove base metals, because most of the time the PGMs are associated with base metals. And then this will be followed by bioprocessing to extract the PGMs. So this was the possible flow sheet that we wanted to follow to get the ore samples, we characterize, and then we subject this to the microorganisms that we would have isolated from the PGM mining site. So in terms of the PGM mining site that we worked with, South Africa is lucky endowed with a lot of mining companies that are working on PGMs. So we worked with Mogalekwena Platinum Mine, where we sourced some of the samples that we used in the study. We also used some samples from Sibanye Stillwater. So Mogalekwena Platinum Mine, the type of PGM samples or PGM deposit that you find there, I have the blood reef deposit, whereas the Sibanye is the UG2 deposit. So you'll find that the mineralogy of these two samples are quite different, the blood reef and the UG2, which also has got an influence in terms of how you approach your extraction process. So we collected samples from there and then we characterized them. So in terms of the isolation and the identification of the microorganisms, we found that we were able to isolate some bacterial isolates and also some fungal isolates, which we then did some characterization and also screening and isolation, and we finally did some optimization studies to try to find out which are the microorganisms that were giving us better organics, and also because of the PGMs being able to only, you find that with the PGMs, you are only going to be able to get them into solution through chlorides, and also, but then it's very difficult to be able to find microorganisms that will give you chloride solution. And the only microorganisms that we're able to identify from the samples that we collected were the ones that could give us cyanide. And we know that cyanide can complex with PGMs in the same way that cyanide complexes with gold. So you find that the chemical equation for the complexation of PGMs with cyanide is actually similar to the one that we see with the gold. So we then decided that we were going to work with this sample, with the cyanide producing microorganisms. Then the first thing that we did was to characterize the samples that we were going to be using. And as you can see, the PGMs are largely associated with sulfides, base metal sulfides like pentlandite, chalcopyrite, pyrrhotite. So for you to be able to target or to get into the PGMs, we then need to firstly destroy these base metals so that you can then be able to then bioleach your PGMs. And the other important thing to note is that chalcopyrite or copper tends to also form strong ligands with cyanide. So if you want to make sure that you are not going to be using a lot of cyanide, you then need to remove the copper first before you then do the PGM leaching. So it was then important for us to realize that we needed to use a two-step process here in order to first remove the base metals before we then target the PGMs. So our mineralogical characterization highlighted a few things, that the PGMs are strongly associated with base metal sulfides, and that also gave us an idea in terms of the processing route that we would follow. So the presence of base metals in the PGM ores present challenges such as locking up of the PGEs in refractory sulfide matrices, and also the fact that we know that copper tends to react with cyanide, so it was going to be able to compete with the PGEs when we do the cyanide leaching downstream. So this was also going to have an impact in terms of the reagent consumption. And knowing that when you are generating cyanide using biological microorganisms, the quantity that you are going to generate is not going to be a lot like you would if you are using chemical cyanide. So we knew that we needed to take out the base metals first before we do the PGM leaching. So we then did a pre-treatment process to try to remove the base metals first, like the copper and the nickel and the cobalt sulfides that were associated with the PGMs. In that manner, we would then lower the amount of cyanide that we would then be using downstream, and also would make sure that we recover these base metals if possible. And so the approach firstly was to then remove the base metals using a sulfide oxidizing microorganisms, because these base metals were in the form of sulfides. So there's a paper that has been published that actually talks about this. And this, if you want to read this paper, this is the paper that was published in Minerals Engineering. So after the removal of the base metals, then what would happen? We'd expect that we'll have our liberated PGEs, which will then now react with the biocyanide that we're going to be generating from the microorganisms that we'd isolated from the mine site. So we'll then generate biocyanide, which we'll then use to bioleach the PGMs. That was our expectations. So in terms of the base metal extraction, using the sulfide and ion oxidizing microorganisms, we're able to extract about 81% cobalt, 6% chromium, 84.6% copper, about 20.5% iron, and 88.3% nickel. So the base metal extraction was it occurred very, very well. The yield was very, very high. So after we had done the base metal extraction, we then used the residues to then recover the PGM. So this is actually the overall process flow sheet that was then developed, where you recover the base metals first, and then you take the base metal free residue, and then you expose it to biogenic cyanide. So we would then produce the cyanide using the microorganisms that we'd isolated, and then use the cyanide to then recover the PGMs. So the process itself, so these are the major processes: the removal of base metals, and then followed by the bioleaching of the residue-free base metals free residue in order to recover the PGMs. So in terms of the recoveries, unfortunately, like I said in the beginning, that PGMs are very tough to extract. So in terms of the recovery, under atmospheric conditions, we're only able to extract about 0.3% platinum, 0.3% palladium, 17.9% rhodium, and then about 91.03% gold. And then we tried to then use pressure leaching at the same time to see if we could then improve the recoveries, and we're able to only extract 4% platinum, 38.5% palladium, 11.6% rhodium, and 92.1% gold. So as you can see, you can be able to extract a lot of gold, but in terms of platinum and palladium, because of the high potentials or oxidation potentials of these metals, it's actually still very difficult to extract them using this particular process. So this is the work that we've been working on in terms of bioleaching of PGMs, the critical metals or the most important metals on the South African mining environment. And I think I've taken 10 minutes, I think. Thank you so much.
Great. Thank you very much, Sela. So I'd like to invite all of our participants to join back into the discussion and turn on your cameras. So in the time that we have left, we wanted to open up the floor for more of a fluid discussion. If you have any remarks that some of the other presenters' presentations brought up, feel free to jump in. Otherwise, I had a first thing that sprung to mind, which is that we saw 2 cases here of bioleaching of base metal sulfides. And I guess that's kind of the most typical example that we see of bioleaching at a commercial scale. And Patrick, you mentioned that this is often because it kind of makes logical sense because we see the acid mine drainage already taking place. And so it's kind of a logical next step. I'm curious, Nadia, is your work at BIORECO also focusing on base metal sulfides, or are you looking at other materials as well?
Given that sulfide bioleaching is best established, these are the easiest materials that we are targeting. The ore that we process here in Sudbury is a sulfide, so a nickel sulfide, hence the petlandite and pyrrhotite pyrite-rich tailings material that we're reprocessing. But certainly, as outlined by Selo, there's lots of opportunities to expand into other materials. So they're the low-hanging fruit, okay. And then we move on to the more refractory materials from there.
Okay, great. And then another question that was raised by you, Nadia, and also Patrick, that you raised, is the need to reprocess the rest of the waste once we've extracted whatever valuable metals that may be included in there, if that's cobalt, copper, nickel, things, base metals like that. What are some of the solutions that you are looking at in your research to valorize the rest of the material, or at least to treat it in a way that can be as safe and as that limits the damage on the environment as best as possible? Patrick, would you like to expand on that?
I can start. Well, there is two aspects. When you look at the KCC case, the one I presented, as I told you, we did the treatment, we produced some metals, and there was so much value in the metals that the plant itself was profitable. And the waste that was generated is still in place. It's jarosite, hydroxide, there is some calcite as well. I mean, it's still in place. It's quite safe because, of course, there is no metals and the acidity potential is removed. So, in that case, the fact that you don't treat the remaining waste was not that detrimental, as long as you have the place to store safely your waste. But because the value was very important, if you want to develop the solution, it's not the only driver. And if the driver is remediation action, depending in which country you're going to do it and in which type of environment, then using more than only the value, the metal value, is critical and can be critical. And so, so yes, we do, and especially in Europe, there is a couple of projects looking at that. in the past, and for example, one of them where we were involved was called NEMO project, and in NEMO project, one aspect was to treat sulfidic waste using bioleaching, but the idea was to valorize not only the metals but also the waste generated by the process in the other construction materials, all type of construction. So it's more or less what I can say. You know, it's not absolutely necessary, but you cannot, if you put that as a remediation action, just take the value and not take into account the remaining waste. And I will leave my colleagues to complete on that. Sorry, I'm very chatty.
I might quickly add to that it really is part of the discussions that we're having with the Canadian mining sectors, that we will be remiss if we don't tackle the other components and merely take out the 1% value that remains in these materials. They've been stockpiled for so long. There is so much liability associated with the volume of material and the acid mine drainage potential that actually the largest part of our work is tackling, in our case with the pyrrhotite, the iron and sulfur components, producing either an elemental sulfur or a sulfuric acid precursor, an iron oxide product that can be used for green steel production, and not returning those high-risk elements back into the stockpile. And if we're already going that far, if we can separate out those two elements, what we have left over are these cleaner silicate materials that Patrick mentioned can be used as building materials without that iron acid potential. So we really, if we're going to bother digging it all up, we really should be looking at a larger, more holistic zero waste solution. And in Canada, that is a lot of the time, that's where our conversation is starting. So that's where we're at.
Great. Cello, is there anything you'd like to add on this point?
Yeah, I think in South Africa, there's been a lot, especially on the reprocessing of tailings, specifically gold tailings. But I think for us, really, the issue has been that because if you do look at the bioleaching of base metals, you need to have a lot of sulfide component inside in order for the process to be autothermal and be able to be self-sustaining. So the analysis sometimes here shows that the sulfide content is not enough. So now the idea would be for you to try and decompose whatever you have, but that process cannot be self-sustaining enough to be able to run on its own and, on a bioleaching based process. So it's been a bit difficult to actually look at using bioleaching here in South Africa because of those particular reasons. But, in the project that we've been working on, which is the PGM processing, which I highlighted, where we are trying to use biologically produced cyanide. So the idea for us was that, okay, if we use the biological produced cyanide, we know that some of the microorganisms that actually produce the cyanide, they also are able to decompose the cyanide that is produced. So for our case, we're looking at a process which we're thinking that it could be done in such a way that we use microorganisms to produce the cyanide, we use the cyanide to leach the PGMs, and then whatever is remaining, this residual cyanide composition or whatever content is remaining, we still use microorganisms to decompose that cyanide. So in that way, we actually have a more of a closed loop process where we don't leave any cyanide hanging out or dispose of any cyanide into the environment. So that was our approach. But in terms of what is happening in South Africa, you find that bioleaching, there's only one mine actually that uses a bioleaching, where we do bioleaching of gold, and because there's quite a lot of sulfide content in that gold deposit. But most of the stuff, I think that what Nadia has said in terms of, having a more holistic approach in terms of what do you do with the residue, what are the other applications of those residues that are generated, that's the approach that most people are now considering.
Great. Yeah, extremely interesting to hear about this additional benefit of using biocyanide. I wasn't aware of the capacity to break it down as well. So yeah, really promising. Does anyone else want to jump in on this question of closed loop processing and kind of the residuals that are left over after bioleaching, or else I had a few other questions that we were hoping to cover.
Maybe I just want to I think that that's very important what was said. When you have a lot of pyrite as it was the case in Uganda, of course, remaining the acidity and the acid mine drainage was so huge, and the value was so huge, then only doing that, I put the question, is it the ideal case? I think it worked very well, but when you have different type of waste with very little amount of sulfite, for example, well, then you need to include another step, mineral processing step, to try to concentrate it probably. But then, of course, there is less value. So you need, if you want to have profitability and to have a global approach, you need to create value not only from the metals, but from the land, from the materials. You see, you need to add on value to what you're doing, because there is less value in the sulfidic part. So that's very important driver and aspect.
Definitely. And I think that joins up well to what you were mentioning, Nadia, about reducing the liability of mining waste as well, and looking at that as a way to add to the economic argument, I guess, of these approaches. And
it applies to every kind of mining activities nowadays. It's not only bioleaching, or it's not only mining waste. Every new projects have to embark this global view.
Yeah, in Canada, the social license is critical in approving new projects. And if we don't do well on addressing our legacy, and our tailings are now front and center in that discussion on how we deal with that legacy before we accelerate our development and opening of new mines and developing new deposits in mostly pristine environments. And so really, everybody's watching what we do in this reprocessing. Can we move to a zero waste, no liability, no environmental, no social impact solution to be able to provide that social license to build and expand the incredible number of mines that are needed to meet critical minerals demands?
Yeah, certainly a key issue. Sela, would you like to speak a little bit about how WITS is treating these social issues in the type of research that you're doing? Is that something that plays a part in your work?
Well, I think anybody who works in the field has to be concerned about that. So you cannot work in isolation. Even if it's not the core part of your work, you still find that whatever projects you are going to deal with, you have to be able to include that aspect in the whole overall scheme of things. So most of the projects that you find that we do, you have to have a holistic approach to the project, looking at not only the extraction of the value metals, as Patrick has said. You can't just be looking at the extraction of value metals, but you look at what is the impact of the residue or the waste material that you are going to be generating. Because whatever process that you are going to be developing, if it is going to be applied on a commercial scale, that is going to be very important for any mining company to buy that technology that you are developing. They are not only going to be looking at the value metal, but they are going to look at also the environmental impact of any residue that is going to be generated. So the work that we do at VES, I think we basically, you find that we are looking mostly at the extraction of metals, the value metals, but we are also looking at what is the impact of the process itself on the environment. That's why we are very happy to be working on the bioleaching of PGMs, because bioleaching is considered to be one of the processes that has got less impact on the environment, because you are using microorganisms that are already adapted to the environment. And the microorganisms, that if you are going to be looking at the residual content, you are expecting that the microorganisms are not going to produce anything that is also going to be much more harmful to the environment. So the projects that we do here at VES also, they go from they go over the whole value chain in terms of the extraction, leading to what is the impact of the residue that you are going to be dealing with, because ultimately that's what would make people buy the project now. Because like Nadia says, the social responsibilities for most mines, they are more worried about the environmental impact, and also what it will do to the communities around where the mines are located. So we do that a lot, yes.
Patrick, would you like to speak a little bit on the legacy of what remains at the project that you highlighted in your presentation, and how the remediation efforts were completed?
Yeah, I can say a couple of words, and it's actually a very good question, because it's definitely something we would like to study a little bit deeper. The positive aspect, it's that the plant itself, because they needed some energy associated with the plant, a power station was put in place in the area for the plant, but that remains as a legacy, and it still works for the local community and the Cassisi plant. The other positive aspect is that for the moment the plant is still ongoing. There is no more waste to treat, because there were 1 million tons that was treated. And when it's finished, that's the thing with the mining waste. It's when it's not been treated, it's the end of the plant. But the plant is still managed by a reduced team of I think 10 to 15 people, and they are sort of I told you that it was a former copper mine, so they sort of try to think what could be the next step, and the next step could be there is other type of waste in the area. Unfortunately, to a certain extent, or fortunately, I don't know, but they are less concentrate with metal value, because there is less sulfide in it. So the profitability of treating them is of course less obvious, but the danger associated to them is also less important. So it's definitely something they are looking at the moment. So it's really an in-between situation at the moment. The plant is over. They keep the plant for the moment, hoping to reopen some activities in the area. But we're sort of in between two periods. So, but we keep an eye on that, and we keep contact with. Of course, we have a lot of. I have a lot of friends, and still over there, and but for the moment, I would say that the most important legacy was no more acid mine drainage. And that's very important, because I mean, I didn't show you, but the picture, but the all around the area is green again, downstream from the former. That's an important legacy, and especially for the fishermen in the area, that's an important one. The power plant is an important one as well, and the infrastructure as well, because a lot of roads were actually built to allow the process and the plant to be put in place. But again, that's the positive aspect. But at the moment, there is still a plant that they need to think about, whether you close it totally and dismantle it, or you use it again. And there is this 1 million ton of hydroxide and carbonate waste that you need to think about. They're not dangerous, but they're there.
Yeah.
So we're in the middle of the story, I would say.
Okay, great. So I see that time is already running, and we've already almost reached the entire hour. I feel like we could have gone on another hour. But I'd like, just with the time remaining, to give Nadia and then Cello just the chance, if you have any closing remarks on the work you're going to be doing in the next year, and what you're excited to see coming up in the realm of bioleaching.
Well, I think it's an exciting time to be an environmental microbiologist working in mining. The mining industry is going to be looking for, in Canada alone, 800,000 people to work in the industry. And I think biologists actually have a place in that, and working with engineers to design several projects in the next couple of years, and then actually having a very important niche for bioleaching, both for ore processing, reprocessing materials. We didn't even talk about e-wastes or other urban waste that can be reprocessed this way. So it's an exciting time, and I think bioleaching is finally going to have its global heyday, and Canada's finally going to catch up. So that's where we're at.
Exciting, great. Cello, is there anything you'd like to say?
Yes, just I'd like to say we are. I think for us, we are really going to continue working on the PGMs, because like you saw, the recoveries that we're getting are quite a bit not what we're expecting, and we'd like to do some more work and specifically to try to increase the extractions and to see if there's some other way that we can optimize the production of the cyanide that we are producing, because we are also finding that when we do produce the cyanide, to keep it in the species, to keep the species or the phase that we actually want for the bioleaching to take place is actually very difficult. That cyanide species tends to dissociate and form other species. So we want to do more research on that. And we are also been looking at the secondary materials, waste material, which is where South Africa is catching up on, because I think like Canada, we are so focused on primary metals because we've been blessed with primary minerals. Underground, we've got lots of that. So we've not really worried too much about secondary minerals, but we know that for sustainability issues, we need to look into that. And I think one of the things that is also going to catch interest, especially with the PGMs, because looking at the PGM prices that have been going down, most PGM miners are very interested in looking at alternative processes in order to lower the process costs. So we would really want to work on this. And for us, we found out that something that we found out was that actually having engineers and microbiologists work together is actually the best combination, because the other people focus on the engineering aspects, and then the microbiologists tell you much more about how you can modify or optimize the microorganisms to work better. So this project for us has been very good in that way, in that we've worked together, and we hope that we can also continue to work with other microbiologists on an international scale, so that we can understand the engineering and the microbiological aspect better, so that we can make this process work better.
Excellent.
That's it, right? Yeah.
Great. Thank you so much. So yeah, I see that we've already run a little bit over time. So I guess I'd like to thank again all of our speakers for the 3 really insightful presentations. I think it's really a joy to hear about kind of intersecting research from around the world, and it all seems quite promising. So I hope this is only the beginning of the discussion, and that we'll remain in touch. We have more information that's available about the BioRecover project on our website. That's biorecover.eu, for anyone in the audience who isn't familiar with the project. And yeah, I will keep in touch and keep everyone informed about the final results of our project. And hopefully there will be a lot more research in the future on this topic. So thanks everyone for your time.
Thank you.
Thank you. Thank you. Bye-bye.
Okay. Bye-bye.
Bye.